What's up, everybody? In this video, I'm going to go over the process of dissociation, net ionic equations, and solubility rules. That's a lot of stuff, so clear your desk, take your notebook, and make sure you take detailed notes. There's a lot of stuff I'm going to be covering today. So the first topic I'm going to tackle is dissociation. Before I jump into this topic, I will be using a lot of vocabulary that may be new. I expect you guys to pause the video and note down the meaning or definition that I give, since I may not always write it out on the screen. So, as I have probably mentioned in the class by now, dissociation is the splitting up of two oppositely charged ions that are held together by electrostatic force of attraction. For dissociation to take place, the ionic compound must be dissolved in a polar solvent, which is almost always water. Now let's take an example of salt, sodium chloride, and see how it will dissociate when you add it to water. So as you can see on the screen, I have a molecule of sodium chloride. You will notice that the sodium ion, which is positively charged, and the chloride ion, which is negatively charged, are held together due to electrostatic forces of attraction. Remember, they are opposite charges, and so they attract each other, and that's how the molecule sticks together. And so every time you look at a solid crystal powder of sodium chloride, this is how all the molecules are. They are oppositely charged ions that are attracted to each other. Now, what does adding water to this compound do? Water, being a polar molecule, can pull the oppositely charged ions that are sticking to each other like magnets away from each other. These ions are coated with water molecules from all sides and cannot feel the electrostatic force of attraction anymore. And so that means that this sodium ion and this chloride ion are now going to be covered with water molecules from all sides. So imagine this is like a layer of water molecules that is coating both of the ions. And now because they're coated with these water molecules, sodium, for all intensive purposes, has no idea that there is a oppositely charged molecule right next to it. And so this is how salt stays dissolved in water. Once you dissolve salt in water, it is going to stay that way unless you just evaporate the water and then the salt turns back into a solid form. So this is dissociation. Now, if you understand this concept, then it should be really simple to understand why don't all ionic compounds dissolve in water. So let's take an example of something that does not dissolve in water. I'm not sure if I have already talked about how to read the solubility chart, which is this portion right here. So I'm going to go over this one more time and review this real quick so that you'll have a better understanding of how to figure out if a compound will dissolve in water or will it stay insoluble. You will notice that this chart is split into two sections. Section 1 is for soluble compounds. Section 2 is for insoluble compounds. And so let's look at these soluble compounds first. So according to this chart, it says soluble compounds contain. Now what this means is that as long as you have these anions in your chemical, then all of these compounds are going to dissolve in water. So what does that really mean? Let's take an example of this anion. I hope by now you know that this anion is called nitrate. So what you need to know is that as long as the name of the chemical that you're looking at ends with the word nitrate, it doesn't really matter what the first word of the chemical is. It could be literally anything, like it could be sodium, and you will have sodium nitrate. Wow, I just misspelled it. Sorry about that. And so sodium nitrate will be soluble in water. I can do the same thing. I can erase the sodium part, and instead I can write silver nitrate, and this will also be soluble in water. And here's why. If you look under the column of common exceptions, you know that nitrate has no exception. It means that as long as the chemical you're looking at has the word nitrate, then all the compounds will be soluble. Now let's take a look at something like chlorine, for example. Now you know that chlorine is also under the soluble compound list. It also means that as long as the second word of the chemical ends with chloride, let me make sure I spell it correctly. Okay, chloride, then the compound will be soluble. So I can, for the first word, I can write potassium, and that will give me potassium chloride, and potassium chloride is soluble in water. I can also write iron, and that will also be soluble in water. However, what if I take a different example and I write silver? Now at this point, I want you to pay attention to the common exceptions list. You will notice that silver is listed as an exception. That means that if silver is bonded to chloride, then this compound is going to be insoluble. This is not going to dissolve in charts. So say for example, here's our solubility chart, in which we will notice that nitrate, which is our anion in silver nitrate, and chloride, which is our anion in silver sodium chloride, are both soluble. What does this mean? And let's take a look at nitrate and chloride. However, now nitrate has combined with sodium, but because nitrate has no exceptions, sodium nitrate is still going to remain soluble. However, what about my chloride? Now chloride does have an exception. Well, it has three exceptions, and one of them is silver. It means that my silver chloride is... Now that we understand that silver chloride is insoluble in water, and we have hopefully also understood how to figure out if something will dissolve in water or not, let's try to understand in a little more detail as to why doesn't silver chloride dissociate in water. So let's say you take silver chloride, which is AgCl, a white colored solid powder, and you add it to a test tube, and then you put some water on top, and you take a glass rod and you start stirring. Now what you will notice is that it doesn't matter how long you stir the solution or the mixture, the silver chloride will stay insoluble. It will not dissolve in water. So let's take a look at why does this happen. You will notice that just like sodium chloride, you have your silver ion, which is a positive ion, and chloride ion, which is a negative ion, and they are attracted towards each other by a strong electrostatic force of attraction, just like a magnet. Now, what happens when you add water? Water, when it comes to sodium chloride, was able to pull these away from each other, right? So this went separate ways and this went separate ways. However, in case of silver chloride, this unfortunately doesn't happen. Water is simply not strong enough to break the force of attraction between silver ion and chloride ion, and as a result you have nothing. You do not break this bond, and so this stays intact, and as a result you have no dissociation. Okay, and so what do we take away from this? We can be confident in saying that if an ionic compound wants to dissolve in water, then it must dissociate. Okay, so dissociation equals solubility. No dissociation means no solubility. The last topic I'm going to cover is net ionic equations. And so for this concept, let's take an example of two chemicals that we will be adding together, and that is sodium chloride and silver nitrate. Every time you see an equation like this with two ionic compounds reacting with each other, the first thing you need to do is go back to you have these two chemicals, sodium chloride and silver nitrate. They are both soluble. Okay, so as soon as you dissolve these two chemicals in water, both of them will dissociate and dissolve in water. Now, what happens when both of them dissolve in the same sample of water? As soon as you add the sodium chloride, it is going to split into the sodium ion and the chloride ion. Similarly, AgNO3 is going to split into Ag, and I forgot to add the signs here, so let me go ahead and do that real quick. Ag positive and NO3 negative. So at this point, you have two chemicals, sodium chloride and silver nitrate, that you added to water together, and both of them have dissolved. Now, what's going to happen? This sodium ion and this nitrate ion and this silver ion and this chloride ions are going to combine. So that and that. At this point, we need to go back to our solubility chart again. The word is precipitate. Okay, so how is this reaction going to look like? Notice that I made an arrow pointing downwards. This arrow tells me that this chemical is insoluble. And obviously, if something is insoluble in the water, it is going to appear in the solution. What does that mean? Think about what happens when you add sodium chloride to water. The sodium chloride, quote unquote, disappears. And so suddenly, if somehow that sodium chloride was insoluble in water, then you will say that it reappears. And so AgCl is an insoluble compound, and it has formed what we call a precipitate. A precipitate is a compound. A precipitate is a product, rather, that is formed as a result of a chemical reaction, and that product is always insoluble in water. Okay, so precipitate is always insoluble. Now, as we write this equation down, I'm going to tell you that this equation is 99% correct. You know that all of this process was taking part in water, right? Now, all the sodium chloride is gone, all the silver nitrate is gone. What you do have is AgCl, which is a product that is insoluble. But what about this silver nitrate? You guys know that nitrate is always soluble. So what happens to the sodium nitrate? This sodium nitrate is going to stay as sodium ions and nitrate ions. And you will notice that this sodium ions are the same as these sodium ions, and these nitrate ions are the same as these nitrate ions. And so if you really think about it, the sodium ions and the nitrate ions, didn't do anything in this reaction other than dissociating, and that's it. And so since these ions didn't do anything, we call them spectator ions. This term, spectator ions, is very important, and it is going to be a key factor in being able to identify if a chemical reaction takes place or not. It is also going to be very important while writing net ionic equations. So, the topic is net ionic equations. We haven't written our net ionic equation yet. So, I'm going to erase all of this and I'm going to rewrite the equation that I started with in the net ionic equation form. In order to do that, I need to write sodium chloride in its dissociated form, and I need to write silver nitrate in its dissociated form. Doing so give me Na positive plus Cl negative plus Ag positive plus NO3 negatives. And so what I have done is I took all my ions and I wrote them in a dissociated form. Now, what am I going to get? I'm going to get sodium ions plus nitrate ions plus silver chloride followed by a downward facing arrow. If you were to compare this equation and this equation, you will notice that they're basically the same equation. It's just that I took all my reactants and I dissociated them. Now, we're going to cancel things out. You will notice that I have sodium ion here and I have sodium ion here. So they cancel each other out. I have nitrate ion here and I have nitrate ion here. So they too cancel each other out. After canceling these out, what am I left with? I am left with Ag positive, Cl negative, and I'm AgCl as the precipitate. So now we will write our final net ionic equation, and that is going to look like something like this. Ag positive plus Cl negative yields AgCl with a downward arrow, and this is your net ionic equation. All right, so we are going to do a bunch of examples like these in class, so please make sure that you watch this video and you take proper notes. These notes will be graded as a daily grade, so please make sure that you get it done, and I will see you in class.